Hello, everyone. How is GDC going so far? Good? Yeah? Okay, cool. It's very nice to have you. I'm sorry for you having me again, but I won't be long. I'm with some friends here. So we're going to talk about rendering, performance, and customization in Unity 6. So I'm product manager for graphics. I'm Mathieu Müller. Damien here, who is a product manager for graphics as well. Adrien, who is a developer on graphics as well. And Ludovic, who is developer on the VFX Graph team. So what we're going to cover rendering performance improvements, render graph for the universal render pipeline, ray tracing APIs, and custom HLSL blocks for VFX Graph. So let's start with a big overview of all the optimizations that we've done in the past years on render pipelines. Everything which is in bold, I don't know if you see it very clearly, and has a small Unity 6 logo, are things that are in Unity 6. So as you can see, we've done a lot of optimizations. So we start from the left with CPU, starting from the CPU, then going to the GPU, compute, low-level optimizations on mobile, and finishing like rendering the final pixels. So what we've done, so on the CPU side, first we've optimized the volume system. We have the SRP batcher, which has been here for a long time already, which is not new. We have the GPU resident drawer, so we will talk more about this as well, which is changing the way we are processing the scene. So we are parallelizing the processing of the scene on the CPU, and then putting this into a large buffer, and then using it on the GPU. So it's GPU-driven techniques. We have also parallelized the way we are sending jobs on the X12, so we split graphics jobs. And we have optimized the CPU performance when you're using multiple VFX instances. On HDRP, we have done a lot of work in the past 2-3 years to parallelize the light loop using burst and the job system. And we have shadow caching part of these optimizations. So let's move to the GPU. So as I was mentioning, now we are treating larger buffers directly on the GPU, so we could add GPU occlusion culling, which will automatically discard like the non-visible geometry. We have batch GPU skinning, so that we can parallelize the treatment of skin meshes on the GPU. And then when we move a bit further for the render loops, we have render graph, which was introduced in HDRP initially, and now is as well and new on URP. And Damien will talk a lot on this, and Adrien will make a demonstration of how to use it. For URP, we have been also spending a lot of time optimizing forward plus, and deferred, again in Unity 6. And for the GPU resident drawer, right now in Unity 6, it's compatible only with forward plus. And then on the renderer, same thing. We've been working with a lot of projects to try to optimize the hybrid type cluster render loop of HDRP. I don't know if you've seen that there is a line URP and the bottom is HDRP, right? And then when we move a bit further, leveraging compute systems, so VFX Graph has now almost feature parity between URP and HDRP. So it's a way to leverage compute on a lot of platforms for VFX. And HDRP was designed from the ground up to have everything running compute. Then, if we move one step further and we go to very low-level optimizations, one advantage of render graph is to be able to leverage native render passes so that we can have much better performance on mobile. Adrien, again, will touch on this, and Damien as well. And then finally, when you have your final pixels, you want to keep the shading quality, or you have like 4K to render, so you need to be able to choose exactly what you want to, like the quality of shading that you want to have. So we have first foveated rendering coming in Unity 6 for XR. And then we have dynamic resolutions. We already had some upscalers. For example, AMD Fidelity FX FSR was already available for all pipelines. But now we have STP, so Spatial-Temporal Post-Processing, which is our own upscaler. And the novelty of this is that it runs across a lot of platforms. I will touch on this a bit later on. And then we have a few ones which are exclusive to HDRP, AMD Fidelity FX FSR2, and NVIDIA DLSS. Is that clear? I'm not too fast. It's okay. So let's start with the volume framework. So as I was mentioning, like it was introduced first on HDRP, then we added it to URP, and one big problem to make it first citizen was performance. So we optimized the performance so that you can use the volume system even on mobile. But we also aligned the frameworks and improved the global UX. So we'll show you a bit how this works. So now, if you go in project settings, in graphics, you can find a general volume that will apply to the entire project. So for example, let's say you want to desaturate your entire project. You can do it at this place, and it will just do for your entire project. So it's a nice place to give all your default settings. Then you can go in quality settings, and we can go on the universal pipeline asset, or it could be the same for the HDRP asset. And same thing here, you can see at the bottom that we have a volume, so you can override your volume per quality settings. So for example, here on the high quality settings, we have a vignette that wouldn't be, for example, in a lower quality setting. And then finally, in the scene, you can put volumes, either global ones or local ones, so that you can have different volume impact depending on where you are. So for example, here, we have an indoor volume, and that is changing the exposure indoor. And if you want to verify, because that's the problem of these systems to have them stack, is that you never know where the value is coming from. So if you go to Window, Analysis, and Rendering Debugger, which is, again, something from SRPs, you have a volume debugger. So you can, let's enter play mode here, for example. So you can choose your camera. So here, the main camera. We will look, for example, at the color adjustments. And you can see here at the bottom that we have the default volume where the post-exposure is 0. Then we have the SRP asset, which is per quality asset, where there is no override because we are not overriding it. And then we have the outdoor volume, which puts the exposure at 1. But here we see that it's applied to 0%, and the indoor volume is at 100%. So if I go out, we will see that suddenly we have these values being interpolated because we're using the two volumes, right? So it's a very nice way to use this volume system. It's very powerful for your scalability. For the GPU resident drawer, so what it is, it would be too long to explain, but I really recommend, if you want to know the details, to look at the batch renderer group. So batch renderer groups was a system which was introduced for graphics entities, for dots initially, to be able to parallelize the treatment of the scene. And you can check this blog post, which gives a lot of details, and also comes with a project that you can build, which allows to see how you can leverage a batch renderer group in your custom systems. But the problem was, like, we didn't want to ask everybody to move to dots to be able to have good performance, right? So we wanted to have batch renderer groups available for game objects. So if we want to summarize what it is, we will take the scene using the job system to parallelize the processing and put everything into large buffers that you see here that we will send to the GPU, and then we will actually render the scene on the GPU. So it's very easy to, it gives huge performance improvements. The more you have instances, the more you have improvements. But even on scenes like the URP samples that we have, we saw even improvements in simple scenes like this. So let's see, it's very easy to set up. Again, you go to project settings, like here for URP, and then you have the GPU resident drawer, which is here, and we can look at the stats, for example, and basically it will allow to treat the scene differently. So here we have two. Let's go back inside. We have 3,000 batches, right? Now we can just enable it, and we are down to 1,000 batches, which is automatic for you. So very, very easy to use. Okay, so yeah, that's what I was mentioning, available for both HDRP and URP. And next is occlusion culling. So same thing, very easy to activate. You will see the number of triangles going very low now because we have almost 1 million triangles here because we are rendering all the triangles. Now if we activate GPU occlusion, we see that it's going down. And the way it's working, it's that we are rendering an extra pass. We can also debug that in the GPU resident drawer. So we can visualize exactly how the occlusion is working per frame. So if we move around, we see that it kind of like hides all the objects which are behind these squares. And it's not always a win, be careful, because if you're not bound by these vertices, then it wouldn't give extra performance, and it has a cost because there is an extra pass to create this visibility buffer. So it's not always a magic bullet, but it's here. Next, so I was talking about batch GPU skinning. So where it is, it's in the player settings. Before you had the choice between CPU skinning or GPU skinning. Now you have GPU batched. And I want to mention here that this is a kind of features that web GPU give access to together with VFX Graph. Here you see VFX Graph running on web GPU. Split graphics job. So again, we had multiple ways of treating the graphics jobs on DirectX 12. So same player settings. You can choose between native, which was the initial DX12 implementation, then legacy, and then we have this new mode called split that you can see here, which is of course the winner. That's again a very simple one. And I will finish with STP. So STP is really like this really super magical stuff, you will see. It's very impressive. And it's very simple to use. So the idea here is like you have the render scale in the global settings, in the quality settings, and you can choose your upscaling filter. And now we can use, for example, spatial-temporal post-processing here. And so I will try to get you watch that. Maybe I will go 4K to really go crazy. So we have 4K, right? Now we will just diminish. So just to show you what it does, we have again a debugging mode. So if you go in rendering, you can go and visualize the STP upscale. So here we see that we are rendering at full scale. When I will diminish the render scale here, we see that we render at quarter of the resolution, right? But what is interesting here is that you should must not see any difference going from a quarter resolution and full resolution. Okay, I do it again. And we will see when I move around, it looks like it's actually rendering at full resolution. We can see that we can push it really further, because sometimes we don't even know if it works. So when you do it like 1/3, you would say it will be very ugly, right? We are actually running at this size, and it still looks like this, which is pretty crazy. And really many times I was like, it's not working. So let's put it to 10%, right? And it's still like, it's not working. But then you're like, if you really go outside, we can see that there is still some shimmering on the side. But it's just to tell you that rendering at 10% of the screen still has this amazing final quality because we are accumulating the frame. And what is very impressive on this, we can use the display stats, which is a bit hidden because it's only on play mode on the rendering debugger, but I really recommend checking this. If you look at the GPU frame, we are running at 4K. We have about 4 milliseconds because we're running small. Let's move to 0.5. We are at 5 milliseconds. If we would be at 1, no, not 51, here, we will see that it will be 80 milliseconds on the GPU frame, right? Just because you've saved all this time by rendering at a quarter of the resolution. So basically that's it for the improvements, and we will move to render graph. So graphics customization.
Matthew. I'm Damien, graphics product manager at Unity, and in this section of the talk, we'll discuss graphics customization and the new render graph system in Unity 6. So first of all, Unity's scriptable render pipelines are highly customizable, which provides us with deep control over the game's graphics rendering, so we can control the look and performance of our game. Sons of the Forest by End Night Games uses the high-definition render pipeline to render large, dense, beautifully lit environments which players can explore, build their own constructs and bases in the world. And Dave the Diver by Mintracket uses the universal rendering pipeline to render a unique blend of 3D graphics and pixel art. And another great example is Warhammer 40K Rogue Trader by All Cat Games, which implements a custom scriptable render pipeline to really deliver the look and atmosphere of its franchise. Both the universal and high-definition render pipelines provide a large collection of ready-made effects, such as reflections, shadows, lens flare, fog, and many more. But sometimes you may want to create your own customized versions of these effects or your own unique specialized effects for your own use cases, which may be tied to your game's mechanics. Here we have a nice example of the game Viewfinder by Said Al Studios, which implements a unique photo-to-world effect that is tied to the game's puzzle mechanics. To be able to create our own custom effects, we often need to be able to write our own custom rendering passes and inject them within the render pipeline. Here we have a simple example of a color inversion pass, which simply inverts the contents of the color buffer. Here we inject it after the transparency pass. And both URP and HDRP allow us to write custom render passes and custom rendering features and inject them within the pipeline. The custom pass injection workflow is significantly improved with Render Graph, which allows us to extend the pipeline more easily, more reliably, while also improving rendering performance. So first of all, what is Render Graph? Render Graph is not a node-based or graph-based editor like Shader Graph or VFX Graph. It's not a visual editor to create your own render. It is just it is a rendering framework that allows us to maintain the growing complexity of render pipelines. Provides us with a graph-based representation of the pipeline, which describes our render passes, as well as our frame buffer attachments or render targets, as well as the dependencies between passes across the pipeline. And having this information allows the engine to systematically and automatically optimize the pipeline via various mechanisms, such as render pass calling, which will skip unnecessary passes for the frame, or the merging of render passes, which we'll discuss next. But it also allows us to extend the pipeline more easily. To extend the pipeline, we need to be able to inject our own rasterization or compute passes within the pipeline, which we can do with the scriptable render pass API. We then need to be able to set our render attachments, that is the input and output attachments for the pass, so our frame buffer attachments, and then set our necessary render pass data, for example, our shader resources, which we'll use in the pass. To do this, we can use the new context container, which allows us to reference all the render pipeline resources to be used in our pass. So we can access our color buffer, depth buffer, G buffer, or other render targets, and all of our necessary lighting data, camera data, and other pipeline resources. Then we need to be able to inject our graphics rendering or graphics commands. So we may need to set our shader resources or record our draw calls, and we can use the raster command buffer API to do that. We can also do the same for compute passes with the equivalent compute command buffer API. So we can set up our compute shaders and record our compute kernel dispatches in a way that is compatible with Render Graph. Render Graph also introduces support for frame buffer fetch, which allows us to load our input attachments, our frame buffer attachments, directly from on-chip TAL memory. So instead of using texture sampling, we can use frame buffer fetch, which will reduce memory bandwidth usage and improve mobile GPU performance. This optimization is also introduced alongside with rasterization pass merging. So Render Graph will merge compatible passes depending on the dependencies of passes and the use of frame buffer fetch, and create the equivalent native render passes. So depending on the platform, it may be Vulkan render passes on Android or Metal render passes on Apple Silicon. And with the introduction of the Windows on ARM build target, we also have support for DirectX 12 render passes. To better understand the benefit of native render pass merging, we can look at a practical example of deferred rendering. So with deferred rendering, we first have a gbuffer pass, which writes our material parameters to our gbuffer attachments, which we then subsequently load in the lighting pass to perform lighting calculations in our shader. Render Graph is able to merge both the gbuffer and lighting pass as a single merged native render pass. For Vulkan, we'll create two sub-passes. And in the lighting sub-pass, we can load our gbuffer attachments using frame buffer fetch directly from on-chip tile memory. So we reduce frame buffer memory transfers we reduce energy usage and significantly improve mobile GPU performance. Random Graph also introduces the new unsafe pass, which allows us to more easily port and reuse our existing rendering code with the Random Graph system. However, these passes will not benefit from native random pass merging and other raster pass optimizations. So in most cases, we do recommend porting to raster pass. There are some cases where you may want to use unsafe pass if you do not want to benefit from native random passes. Maybe a good example is Bloom, where we have a lot of subsequent passes that need to access essentially arbitrary locations in the frame buffer. Then we have Render Graph Viewer, which is a graphics debug view that allows us to more easily analyze and understand the render pipeline. It provides us basically with a graphic view that allows us to track all of our passes and their order of execution, as well as our render attachments. We can check the resource lifetime, usage of our frame buffer attachments, and the read and write operations, and also track the use of frame buffer fetch via this little icon here. We can also get additional information for each pass, so we can see which passes were successfully merged by Render Graph via this blue line over here. And in this case, we see that both the gbuffer and deferred lighting pass are indeed merged, and all these gbuffer attachments are loaded with frame buffer fetch. And we can also see the frame buffer attachment load and store operations at the beginning and end of each native render pass. And lastly, we can also click the Go to Definition button under each pass, so we can very easily open the pass implementation in the IDE, understand how the pipeline is implemented, and more easily debug our own rendering code. And that's it. Next up, we have an in-depth demo on how to use Render Graph by Adrian. Thank you.
Thank you, Damien. Hello, everyone. Thank you for joining us for this presentation. So today, I would like to show you how to use Render Graph in ERP in order to implement and optimize a custom post-processing effect. So this is the dither effect that you can see on this slide. So first, we're going to see the effect in action in ERP without Render Graph enabled. Then we're going to port this effect into Render Graph. Once it's done, we can analyze its implementation using the Render Graph viewer in the editor. And finally, we'll try to find ways to optimize this. Let's get started. So first thing is I'm going to open the editor. So this is the terminal scene of the ERP 3D samples. So you can see that my effect is already in action. A custom pass in ERP is called a scriptable render feature. So we have a full screen scriptable render feature here. It's connected to a local volume positioned at the Unity sphere, here at the center of my screen. And if I move away from the sphere, you will see that my effect will be disabled. There you go. And then back again. So it's connected to ERP through the renderer asset. So you can see the effect at the bottom, dither effect. It's injected after the ERP post-process pass. The shader has been made with shader graph, and it requires the ERP color buffer. Now, if I go into its implementation, so let's go into the code. So I'm going to open the editor, and yeah, so this is the scriptable render feature. It's a pretty classic one, so I won't go through all of this, but we can look at the execute function where we're actually rendering anything. So you can see at the beginning that there is this check, and if we're not in range of the Unity sphere, we will just discard the effects. And then there is the rendering itself. So it's a ping-pong blitz. So it's two passes, basically. The first pass is going to take the ERP color target and copy it into a temporary color texture, while the second pass is going to apply the effect. So it's going to sample the temporary color texture that we just made and apply the effect to the ERP camera color target. OK, let's try to port it to Render Graph. So I'm going to go back to the editor, because the first thing to do is to enable Render Graph. So to do so, I will go into project settings at the bottom of my screen. I will go down into ERP settings, and then you will see that there is a compatibility mode. So we need to disable this thing to enable Render Graph. OK, so now you can see that the effect is gone. And that's because we're not recording the effect yet into Render Graph. So the first thing to do is to go back to the code and enable the effect. To do so, I'm going to uncomment this function called record render graph. So you can see that there is already a skeleton for my ping-pong blitz. So there is the copy pass here, and then the effect pass here. So those two passes are made by using the add raster render pass API from render graph. It's going to return as a builder, and with this builder, we will be able to build this raster render pass. Let's focus on the copy pass for now. So the copy pass reads the URP camera color target and writes to a temporary color texture. So the first thing to do is to get access to the URP camera color targets. To do so, I can use the context container here, which is passed as a parameter. So it's called frame data in my function. So I'm going to uncomment this line here, and from the frame data, I will obtain the resource data. And this resource data is containing the handles to the different URP buffers that I can use. So the URP camera color target is called active color texture in our case. Then I can use the use texture API from render graph to notify the render graph that this texture will be used as the input texture for my pass. Then we need to set the output texture, so the color buffer for this pass. So I'm going to use the set render attachment API, and I will use the temporary color texture as my output for the copy pass. But this texture is not existing yet. So then I need to go back here and create this texture. So I can use the render graph API, create texture function. It's going to take as input a texture descriptor. So I can just reuse the URP color texture descriptor and copy it, and I will just rename it so it's going to be visible in the render graph viewer that we're actually using this temporary color texture. Okay. Now I can go to the set render function. So right now I need to enable the execute function for my pass. So I'm going to do so by using the set render function, and the execute function itself is this one. And that's the one we have been using for the non-render graph path, if you remember, because we're basically doing the same thing. We're just copying the URP camera color target into a temporary color texture. One thing to notice is the fact that we're passing the parameters through this structure called pass data. And that's because the execute step of the render graph is happening later in the process, not during the recording. So that's why we need to save its parameters into this structure. And we're going to save the sample texture, which is the URP camera target, here. All right. So we can move to the next function, the next pass, sorry. It's going to be faster because we're more or less doing the same thing. So this time, for the effect pass, we're sampling the temporary color texture, and we're applying the dither effect material to the URP camera color target. So the material is saved here, as you can see. All right. So I think I have everything. I'm just going to save. Let's go back to the editor. So hopefully we should be able to see the effect in action with render graph. Fingers crossed. Yes, nice. It's working. Cool. So now I'm just going to try to move a bit just to see if it's working. Yes, everything is fine. Okay, so then I can have a look at the render graph viewer. So the render graph viewer is going to give me information about all the passes that are happening for the rendering of this frame. So you can see, I'm going to select the main camera. Okay, nice. Oh, okay. So you can see all the URP passes which are rendered into this frame. And at the end, there is the URP post-process pass. And as expected, right after, there are my two passes for my ping-pong blitz. So there is the copy pass and the effect pass. Now, I can stop this. And if I click on the copy pass, I can see its connections with the resources. So I will go down, and I can see that it's reading the URP camera color targets. So you can see the resource name on the left side, and it's writing to the temporary color texture. For the second pass, as expected, the effect pass is reading the temporary color texture that we just made and writing back with the dither effect into the URP camera color target. Okay, so this is great. Everything is working. But one thing is still annoying me, though. You can see that those passes are not merged together, despite the fact that we have been using the right API to merge passes, raster and the pass. So you can see that they're not matched together, unlike those ones, for example, or those ones. And it's an issue for tile-based hardware, aka mobiles, because basically we will have to load and store the frame buffer between the different passes, and it's not optimal for the bandwidth. So I would like to merge them. Let's try to understand why we're not merging them. So I'm going to click on the URP post-process pass, which is happening right before my custom effect. And I can see on the right side in the pass list the explanation why the pass break is happening. So I'm not able to merge this URP post-process pass with the copy pass because the copy pass is sampling the frame buffer from URP post-process pass. And if I click on the second one, the copy pass is not merged with the effect pass because the effect pass is sampling the output, so the temporary color texture, of my copy pass. Okay, let's go back to the editor and try to optimize this. So I'm going to go here. Okay, so now I can see clearly that it's coming from those calls, use texture. So basically, because we're using use texture, we're notifying the render graph that we will use this texture as input, so we will have to sample this texture within this pass. So render graph knows that, and then it decides to break the passes between the URP post-process pass happening here and my copy pass here, because you need to store it to the system memory before sampling anything. The good news is I don't need to sample anything, because here I just need the pixel value of my previous frame buffer at the exact same screen space coordinates. So I can use frame buffer fetch instruction. To use frame buffer fetch instruction, I'm just going to use set input attachment API. Okay, I can remove this. And then I can also remove the sample texture because I won't sample anything. So I'm going to set it to null. Okay. Then let's go to the second one. So it's basically the same thing here because for the dither effect, I just need the pixel value of my previous frame buffer, so the temporary color texture, at the exact same screen space coordinates. So there is no need to sample here as well. I can just use set input attachments. It's going to be faster now. Okay, and I can also remove the sample texture. Okay. Nice. So now everything should be merged. Let's have a look at the editor again. So go here. So to be honest with you, I'm expecting some hiccup here. Yeah, a black screen, you see. And that's because the shader graph that we're using to implement the dither effect, it's still sampling, as you can see here, while I've been requesting render graph to use frame buffer fetch. So I'm going to just update the render graph, the shader graph, sorry. There you go. Back to the game view. Nice. So the effect is happening now. Perfect. Let's have a look at the render graph viewer to see how it looks like. So I'm just going to move to the main camera again and refresh. Nice. Way better. Look at that. Everything is merged. So the URP post-processing is happening on tile with my custom post-processing, and there is no added load and store of frame buffer. So it's quite optimal for the mobile. And you can see if you go down that we're actually using frame buffer fetch. There's the F symbol here and there. This is great. Then if I click on temporary color texture, I can see that we're not storing it, and it's also memory-less. So that's quite optimal. Everything is on tile. Yeah, memory-less here. Okay. One more thing though. Let's try to consider that we're targeting some low-end mobiles. So I'm going to go back to the project settings and set mobile low quality settings. Okay. And then I'm going to also disable the URP vanilla post-processing because it can be a bit expensive, and I just want to keep my post-processing. Then I can go back to the render viewer. Look at that. So now all the vanilla URP drawing passes are happening on tile in a single native render pass with my custom post-process effect. That's quite optimal for mobile. So you can see there is still a final bit at the end to the back buffer, and that's because on laptop, you cannot use back buffer as an input attachment. But on mobile, you can actually, with the right Vulkan extension. So everything would happen on the back buffer, even my custom post-processing effect. And that would be even better. Okay, so I'm reaching the end of this demo. Before I end up, I just want to show you what we have done in terms of optimizations by just modifying 2 lines. So we went from 3 render passes with no pass merging, so 3 load and 3 store of frame buffers, to a single native render pass with a single frame buffer load and a single frame buffer store. Now think about it. Consider a frame buffer uncompressed with a full HD resolution. Its size is about 8 megabytes. So by modifying those two lines and using render graph to port my effect, which took me about 10 minutes, I've been reducing the bandwidth by about 32 megabytes per frame on mobile. So that's basically it for this demo. If you want to know more, there is this forum post where we're describing render graph in detail for ERP. We're providing some documentation, code samples, other tips. So don't hesitate to go there. And if you have one thing to remember about render graph, that's it. Render graph is good for optimization and customization. Thank you for your time. So now, I'm going to go back to Damien for ray tracing API.
Yeah, thank you, Adrien. Right, in this section, we'll discuss the latest improvements to Unity's ray tracing API in Unity 6. So first of all, the ray tracing API is now in a production-ready state, following a lot of improvements to both stability and performance. And it is mostly used by the high-definition render pipeline to render a large collection of high-fidelity ray tracing effects, such as global illuminations, reflections, shadows, and more. And you can try these effects quickly for yourself using the HDRP sample project from the hub, which now includes new ray tracing quality settings. So you can quickly enable ray tracing effects, configure them, and see how they look. So starting with a quick high-level overview of how the ray tracing API works. So first, we need to be able to populate the acceleration structure, which describes our scene's geometry, and build it on the GPU. At which point we can dispatch our ray generation shader to traverse the acceleration structure. And on intersection, we can invoke our hit shader to perform our lighting calculations, or alternatively, invoke the mist shader to shade the sky or the background. Unity 6, and in collaboration with Microsoft, introduces a large collection of improvements to both the functionality and performance of Unity ray tracing. And the first one we'll discuss is support for DXR 1.1. which introduces inline ray tracing support in shaders. This provides an alternative method of performing ray tracing where we can bind the acceleration structure to our rasterization and compute shaders, at which point we can issue hardware-accelerated ray queries in our shader to traverse the acceleration structure and implement our desired shading functionality. To illustrate this, we made a simple demo, which uses the universal rendering pipeline to implement a custom ray-traced shadow effect. So first we can look at traditional rasterization shadows. We can choose between hard shadows, soft shadows, maybe control the blend of shadows and the depth and normal bias to maybe tweak the shadows a little bit, avoid some artifacts, but we don't have that much control. We can go to our render asset and enable our custom ray-traced shadow renderer feature. And now we basically have our ray-traced shadows, which are physically accurate, good looking, also up close. And since we can control our ray queries in the shader, we can also control the spread of shadows. So we can have very smooth shadows or very sharp shadows. We have a lot of fine-grained control over shadows. To see how this is implemented, we can open Render Graph Viewer, refresh, and we see we have a compute shadow pass, which will use ray queries to traverse the acceleration structure and write to our shadow map texture, which we then blit and blend with the color buffer. We can open our compute shader to see how we actually implement our ray traced shadows. So first thing to note, we need to use the pragma require inline ray tracing directive to make sure we only compile this shader and use it on compatible platforms. Then we're basically reading the depth value from our depth buffer and using it to reproject and calculate the world space position of our pixel, which we use as the origin of the ray query. We then calculate an initial local direction for the ray using some random offset per sample, as well as our shadow spread offset, and transform the ray using our light direction. Then we can simply traverse the acceleration structure, and on intersection, we can write to our shadow variable. We also get the previous frames, shadow variable, and a shadow value, and interpolate between those to accumulate samples over multiple frames and perform some very simple denoising. So in 140 lines of code or so, in our compute shader, we basically have ray traced shadows. So we recommend you check out inline ray tracing, see what kind of interesting effects you can implement. Next up, we have ray traced instancing, which is a CPU performance optimization, conceptually similar to rasterization draw call instancing. It allows us to reduce the CPU resource binding overhead, especially when tracing a lot of repeating meshes and detail. And to understand how this optimization works, where the benefit comes from, we can look at how we traditionally set up our shader table, how we set up ray tracing. So traditionally, we basically add a unique shader record for each instance in the acceleration structure. And then we have to basically bind between these resources when tracing. With instancing support, we only add a single unique shader record for all of the instances that we add using the add instances call. We then can set our per instance data and access it in the ray tracing shader using the instance ID parameter to access our per instance transformation, color, and other properties. Again, we have a simple demo to basically just measure the performance difference. So here we're using the HDRP sample project, using the HDRP path tracer, using our test project. And we can basically measure the performance and compare with and without instancing. Without instancing, we can see performance is fairly low, around 9 FPS or so. And by enabling instancing, we can see our performance here kind of doubled. It would normally be a bit higher, but we have a lot of projects open, so we're using all of our memory and yeah. But usually it will run a little bit faster. But really to just understand how we're setting it up. So we just have a custom script that manages our acceleration structure. We basically create the acceleration structure and clear all the instances and set our calling parameters. And then we can basically populate the acceleration structure with our scenes geometry. And for our procedural geometry, the spheres, if instancing is enabled, we can add all of the sphere instances using a single add instances call, where we also have an array of transformation matrices. We could also set any other instance data we need at this point. Or alternatively, without instancing, we just manually add all these instances one by one. So basically, this would improve our CPU performance. Our actual frame rate will vary depending on whether we're CPU bound or not. But even in this case, we're kind of doubling the performance already. And the path tracer is quite expensive. Next up, we have the new ray tracing acceleration structure build flags. So we can basically choose those in the mesh renderer settings in the inspector. We can choose between the fast trace and fast build flags, which are mutually exclusive, to control the trade-off between ray tracing shader performance and acceleration structure build times. By default, we use the fast trace to improve GPU performance. But in some cases, especially if you have dynamic meshes, like skin mesh renderers, which update every frame, in those cases, you're probably better off using fast build. And both of these flags can be combined with the minimize memory flag to reduce memory usage. We can now track ray tracing memory usage in the frame debugger. For each ray tracing dispatch, we will now display the acceleration structure size. So we can basically track ray tracing memory usage directly in the editor. And to actually reduce memory usage, we implemented a bunch of key optimizations. The first one is based on documented guidelines by NVIDIA, is the introduction of glass compaction, which reduces memory usage for static meshes. We also implemented a custom GPU memory allocator for small blasts to reduce the memory usage for small meshes and detail. And we also have the minimize memory flag, which we previously mentioned. And to test these optimizations, we imported a large scene, around 6.77 million triangles. Without any optimizations, the acceleration structure size was around 450 megabytes. And by enabling blast compaction and the blast allocator, memory usage is down to 150 megabytes. And to further reduce memory usage, we enabled the minimize memory flag, going down to 102 megabytes or so. So we just recommend you check the mesh render settings. Make sure you set the ray tracing mode to static for your static meshes, and also set the acceleration structure build flag to minimize memory as well. And that's it for ray tracing. Next up, we have VFX Graph. Thank you.
Okay, so hi everyone, I'm Ludovic and I'm an engineer in the VFX Graph team, and I'll tell you a bit about the power of customization in Unity 6 in VFX Graph. So first things first, what is VFX Graph? For those of you who are not familiar, VFX Graph is the node-based VFX authoring tool of Unity. It combines the extensibility of graph-based tools and the most traditional stack-based approach of authoring particle systems. Every system made with VFX Graph is fully simulated on the GPU, so it allows you to scale from very small systems to a system containing millions of particles. And by default, we provide a rich library of operators that range from very basic operations like addition, multiplication, texture sampling, to more self-contained behaviors like collisions, turbulence, and following a vector field, for instance. But of course, the library is not unlimited, and that is why in Unity 6 we introduce custom HLSL nodes that enable you to write your own snippets of HLSL code that will be executed inside the computation flow of the graph. So you can write your own code, and it can be very helpful, for instance, if you have a complex chain of operations that is a bit tedious to write, to create by plugging many nodes together, and it is more suited for code. But most importantly, and what I'll focus on, is how how custom HLSL nodes enable you to unlock new behaviors. So custom HLSL blocks and operators show as regular blocks, except they allow you to write your own code that you can edit directly in the editor or in your favorite IDE. And you'll see that in each block, the parameters will be the parameters of the function you selected. So let's have an example directly in the editor. OK, so what we are looking at now is a scene where all the particles on the bottom of the box are mesh particles, and the score is also directed by this VFX graph on the right. So if we play, let's see what happens. So anytime the yellow ball, which is a sphere attached to a rigid body, the score is updated and particles are sticking to the sphere. And this is enabled by the use of custom HLSL nodes. So let's see how it works. The way we use it is to write and read to a buffer, which is the occupancy buffer here, that we plug to our new custom block, the sphere occupancy block. In this block, you can decide what shader file you use. And here we use a file called read-write occupancy. And from this file, you can choose which function you wish to use. So let's have a look at what's inside this file. So this file contains the three methods that were available from the block. And we chose to use the update sphere occupancy one. So our occupancy buffer is very simple. It's a buffer with 5 entries. The first entry counts all the total amount of particles that are stuck to the ball, and each subsequent entry of the buffer is just counting the count for each specific mesh type. So what we do with the custom block is that we atomically increment the first entry of the buffer, and then atomically increment the entry that corresponds to the mesh type. Then what we can do with this buffer is reuse it in another system, our score system here, and we can plug it in another custom operator that is using the same shader file, except we chose a different method here. We plug this operator to our update context that will set the text index, and from the text index, we will update the score here. So every time, the score is updated. Very simple. We also use this buffer in our main system to increase the radius of the representation of the sphere. So I don't know if you can see it, but the more objects are stuck on the sphere, the larger the radius of the rigid body. We also read back the values from this buffer to the CPU using async GPU readback here, and we use these values to update the CPU representation of the sphere. So here it is. It's a pretty simple example leveraging read and write to a buffer that was not possible with vanilla VFX Graph. So now let's move on to a more advanced example.
Maybe kill the ray tracing project, the path tracing project.
Oh, it's fine. It's running. Yeah. So what you're looking at is about 8,000 instances, 8,000 particles orchestrated by this one VFX Graph asset here. All the creatures you see are particles, and we use custom HLSL nodes to control the leg animation, to control the swarm behavior, to control the fact that the creatures are following the height map, and we use it for many other things. But what I want to focus on is the spatial partitioning that we use to enable the swarm effect. So as you can see, the creatures here are avoiding each other, but they also following each other, which gives it this organic look. And to be able to have an interaction with their neighbors, particles need to, we need to create an acceleration structure so that each particle know who's around here, who's around it. So we do this mainly in this custom HLSL block, the spatial binning, that uses a shader file here that we call a grid update. And this block takes into input two buffers, so naive grid data and naive grid count, that represent our uniform cell that stores the acceleration structure. So if we have a look at what this method looks like, we can see it's pretty simple. It takes into input our two buffers and the extent of the map. Then from the position of the particle, we can compute a 2D coordinate to decide which cell we are going to write to. And then we will insert this particle in the cell. To insert the particle in the cell, what we do is similar to the previous example. We do an atomic increment to the counter buffer. And then from the 2D index and the value of the counter, we can write the data, so the position and the velocity in the cell. So then if we move forward to the next step of the simulation, every particle have data about what's surrounding it. And so we can plug these two buffers that we just filled the previous frame and plug them in our swarm update buffer, which is another custom HLSL block with a bunch of parameters. And what this block does is that it's going to loop over all our neighboring cells and compute forces that dictates the avoidance behavior or the grouping behavior. So I won't go into detail, but it's just about looking out where are my neighbors and what speed are they going. So all the parameters of our function are exposed to the block. So if, for instance, I increase the avoidance behavior, the avoidance strength, you'll see how the creatures will get away from each other. And if I remove it to the minimum, they will just run into each other. So that's it for my demo. There is so many things happening in this demo. There's even some gameplay elements happening directed by custom HLSL nodes. But I hope at least it gave you an idea of the power that it can bring. And honestly, I can't wait to see what you're going to do with it. I'll conclude by just telling you to join our mailing list that we'll just show you right now. Yeah, so yeah, thank you all for coming here. Please join our mailing list.
And as well, I don't know.
And maybe if we have time for some questions.
And just to also, it was a very technical one, right? So thank you for trying to follow it. we're going to record it so you can watch it at 0.1x. And it was just really to get you into how much you can customize. I don't know if you've seen, but like now the render pipeline, which was written in C# and like totally hidden, is now totally exposed. You can see it in the view, so you can really understand how it works, even if you don't customize it. But then when you customize it, we even know where you put yourself into the pipeline. So it's a huge advancement. So yeah, I just wanted to conclude on this. So 5 minutes of questions if you want.
So I was wondering about the ray tracing, basically. Will it be will it be available on the URP?
So the ray tracing API itself is pipeline agnostic. That's how in this demo we basically made a custom effect. For Unity 6, there would not, at this moment, be packaged ray tracing effects for URP. However, we are looking and researching on how to implement mobile-friendly, in essence, ray tracing effects, or alternatively providing these sort of effects just for desktop and consoles only for URP. At this moment, these are not scheduled for Unity 6, but we are researching this.
Yeah. Like the demo was on URP already. Like
yes.
you've seen.
Okay,
yeah.
Perfect.
Yeah.
Marvelous. I had a few other questions.
Maybe, because we have some people,
right.
maybe we are after at the QA table if you want to come.
All right.
Yeah, maybe one each, yeah. Thank you.
Hi, I'm just wondering if there are any plans to expand custom pass injection points to give us more fine-grained control over where we want to inject our custom passes?
So you can do that. I don't know if we showed it in the script, but when you create a custom renderer feature, you can select the injection point, like after opaque, after transparent. So you basically select where you can inject your custom passes already in the pipeline.
Are these the same as the ones we have in HDRP right now?
It's similar.
Yeah, it's the same.
Okay,
Pretty much
great,
the
thank
same.
you.
Yeah, and actually the render graph viewer works for both HDRP and URP, so it's kind of like similar.
Oh, cool. Yeah. Awesome, thank you.
Thanks for your presentation. I'm trying to intercept the DirectX rendering pipeline for games that have already been developed to
Can you,
change
move.
Change the projection matrix to a custom projection matrix, then trampoline back into the rendering pipeline. So maybe I'll meet you afterwards, and we can talk about that a little bit more.
Sure
It's
thing.
easier. Good. Okay.
Hi, thank you for your talk today. It was wonderful, honestly. I was curious on the ray tracing algorithm. I saw it works really well for static objects. Does it work as well for dynamically moving objects too? Or how powerful / limited is the ray tracing shadow effect for physics-based moving objects?
Yeah. So you can also ray trace dynamic objects. The question is whether you have basically things like GPU skin mesh renderers where you update the vertex buffer every frame. And if that is the case, ray tracing those is quite expensive since we have to rebuild the acceleration structure every frame. However, you can use the fast build flag to make it somewhat faster, but it's still fairly expensive. That's why you often don't see ray tracing applied to things like animating foliage or things in games. It is a bit of a technical problem that's even wider than Unity, trying to figure out how to solve that.
Okay, thank you so much.
Yeah.
Okay.
Hi, thanks for the speech. I do have some question about the occlusion curling when we first talked about at the beginning of the speech.
Yes.
Occlusion curling. We do mention that it will detect like polygons or object that will be like the cameras do not detect it, right?
Yes.
It's got blocked, right?
Yes.
And then we won't render it at all. We won't try to put it on the screen at all. And could I ask about the performance of that stuff? Because I don't know what's going on deep down in the low levels. Would it like we shooting rays every single frame to detect objects?
It just has one extra pass to compute the visibility buffer. And once you can afford that pass, then it will automatically discard the geometry directly on the GPU. So it's quite
everything gets
it's quite
done
optimized on this one.
Everything gets done in a low level, in the GPU stuff.
Exactly.
Okay.
Yeah.
So there's no ray actually shooting out from the cameras or something.
No.
Okay. Awesome.
No. It's really it's interpolating across frames as well. So it's taken the information from previous frames to accelerate the computation.
So it's like keep learning from the previous.
Exactly.
Oh, okay. Oh, thanks.
Thank you.
Thank you.
Awesome presentation. I saw that you mentioned that that it supports DirectX 12 and DirectX 11. Is there any plans to support Metal and Vulkan?
You mean ray tracing on Vulkan?
Yes.
Yeah, so we are not for Unity 6 probably, but we are looking into this. Again, the question is in terms of applications and being able to actually implement ray tracing effects on mobile and have them be performant. But for desktop, we are looking to actually support this. Not really sure yet if we'll be able to do it for Unity 6 or not, probably not, but we'll have some updates soon on extended platform support for ray tracing.
And what about Metal on macOS?
Same issue. Basically, the main issue we had is that, as far as I'm aware, Metal mostly has support for the inline ray tracing sort of approach and not the ray tracing pipeline, which is used by the high definition render pipeline. But we are researching this as well. Again, probably not for Unity 6, but for future releases, definitely.
Awesome, thanks.
If you want to discuss after, we would be interested to know your usage. Yeah.
Yeah, definitely.
Thank you.
Thank you.
Thanks a lot. I think no more questions. So yeah, we will be out there, and I will be back again for the next session. So.